In order to predict the products of a reaction when we know what the reactants are going to be, we need to recall the general formulas for the different types of equations that we have: synthesis, decomposition, single displacement, double displacement, or combustion. And integrating those two, knowing what we're starting with, what elements we have to begin with, and what compounds we have to begin with, and what sorts of products we should be getting. Should we be getting elements? Should we be getting compounds? One of each? Two of each? Or two of one or the other? Then we can use our oxidation sheet or the original compounds to help determine what oxidation number is present on each of the elements. And this is primarily important mainly if you have transition metals or tin or lead, those multivalent elements that are going to be involved. You also want to remember that your diatomic elements, any element that's by itself, needs to be checked to see if it's one of the 7 diatomic elements. And if it is, when we write the formula for it in the equation, it needs to get a 2 as a subscript automatically. Once we've predicted the formulas for the products, then we need to make sure that the entire equation is balanced. Now we're going to look at 3 different reaction types and being able to predict the properties of those. Combustion reactions, we already know that our products are going to be oxides. For single displacement reactions, this is where you have a free element and it's going to attempt to displace an element from the compound that it's reacting with. But that's only going to be successful if that free element has a higher activity than the element that it would be displacing from the compound. And another way of thinking about activity is reactivity, its tendency to gain or lose electrons. And so in order to determine this, is it more active or not, we're going to need to have some sort of established hierarchy of what elements are more reactive than others. Now we can determine some of that based on periodic trends and what we know about metallic nature of elements and non-metal reactivity, but there is a tool called the activity series which compiles all of those reactivities essentially into 2 lists. And the way that you use the activity series is you compare the position of the free element to the element that it would be displacing on this list. And if the free element is higher, the reaction will occur, the free element will displace the other one, and you will get new products. But if the free element is lower on the list than the element it would be displacing, the reaction will not occur. It does not have sufficient activity to be able to displace the element from the compound. Here you see your activity series. If you look in the metals column, you see at the top we have the alkali metals, lithium, potassium, then you have sodium, a couple more down from that. These are the metals that we would expect to be the most reactive. Towards the bottom you find some of your transition metals, silver, platinum, gold, typically very unreactive metals. So activity is decreasing as we go down these lists. For the nonmetals, the only ones that we have shown here are the halogens, and if you recall, nonmetallic reactivity increases as we go up the column. So you see fluorine being the most reactive nonmetal going downward to iodine, which of these 4 would be the least reactive. With double displacement reactions, usually what we're mixing are 2 aqueous solutions. So it consists of 2 different compounds, usually ionic compounds, that are dissolved in water. And when you have an aqueous solution, those substances that are dissolved actually dissociate from one another. So the cations and the anions are intermingled with one another but are suspended within that solution. When you mix 2 aqueous solutions together, now you have all of those ions intermingling. And when you consider with a double displacement reaction, if you're going to predict what you should be getting, essentially you're swapping the cations between the formulas. Well, those resulting predicted formulas may represent something that is also water soluble. And so, in effect, on the product side, that soluble substance, you still have the ions free floating in solution. However, other times you may get a pairing that represents an insoluble substance, and so that material, those ions, will stay in their molecular form and they will precipitate out of solution if it is an insoluble substance. You may also find the formation of a gas or the formation of water. These are also products that will or can be formed from a double displacement reaction. If it's an insoluble precipitate, then generally it will fall out of solution to the bottom of the container. If it's a heavy enough or large enough particle size, it will fall out reasonably quickly. If a particle size is smaller, then it may stay suspended, look more like a cloudy solution, but eventually it will separate out. Generally, precipitates can be recognized by the fact that their state is listed as S for solid, or you may even see a downward arrow placed after the formula in the equation to signify that the reaction is a precipitation reaction. For decomposition reactions, the exact products that we would predict for these reactions depends upon the type of substance that is decomposing. For instance, carbonates typically decompose to form carbon dioxide gas. So if we have a metallic carbonate such as sodium carbonate, we get the carbon dioxide, that's the given product, but the co-product is also a metallic oxide, and in this case would be sodium oxide. Metallic oxides, specifically here we have listed transition metal oxides, but really for most metallic oxides, what you will get when they decompose is the two elements separated from one another, the metal and oxygen being diatomic. Note that it gets the 2 written after its formula as a subscript automatically. Metallic hydroxides will decompose to form water and a metallic oxide. If you have magnesium hydroxide, your 2 products would be magnesium oxide and water. And metal chlorates will decompose to form oxygen gas as well as metal chlorides. And this is why chlorates should not be stored close to flammable substances, because when they decompose they are a good source of oxygen, and thus in combination with something that's flammable could pose a serious fire hazard. Chlorates are also used as oxidizers in fireworks to provide additional oxygen so that the metallic salts in the fireworks can burn with a brighter color.